Hi, good morning, and welcome to the ZP Developer Zone. So we do this every Thursday at 8 a.m. London time. At the moment, there may be some time zone changes that are going on, so it sort of slightly confuses people, but let me just jump straight into it. So we do this, and we have our ZP Academy. So if you're looking for free courses, there's at least two courses up there on electrochemical techniques. I think it's probably worth looking. There is a few questions that have come in this week. Have a look at the ZP Academy. Don't forget our webinars every Thursday at 8 a.m. London time. Collaborations, these are strictly with often with PhDs and such, like often in sort of regions like the UK where there is public funding for this. We do offer jobs. We do have our ZP Developer Zone. So we were at like USN, which is a university near us, last week. If any of you watch us on YouTube, you'll see that we made a little video because we were at the university and we were sort of recruiting there. And then we also have workshops, and workshops are something we started really in 2022, and they're one of the best ways of getting really good quality information about sensors, biosensors, and everyone gets to make biosensors at the workshops. So we do have some workshops in April, one in Norway, one in the UK. So Horten is a town in Norway. We'll have a workshop there because we have facilities there. We also have facilities in Coventry in the UK. And we're also then having another workshop again in Horten in May. So there's plenty of workshops going on. If you see a link pop up at any point during this webinar, I will have posted it already underneath the video so that you can find these useful links afterwards. Question number one really is a discussion about accuracy of HPLC. HPLC is really accurate if if your sample is very sort of, I want to say, pure or homogeneous. It can be very good, but when you've got heterogeneous samples like chilies, it can be it can be not quite so as accurate, and I'll discuss that. I also want to do a discussion about chemiresistors. Chemiresistors are something that we actually do use at Zimmer and Peacock, and we use it on our CO, our carbon monoxide sensor. So I will do a little discussion about chemiresistors. And in fact, people try to use it. Well, they do use interdigitated electrodes for chemiresistors, and actually, we make a chemiresistor. We don't use interdigitated electrodes. I'll talk about sensors for metallic elements. It's nice that we do get questions that come through our YouTube channel. So there's lots of channels or lots of ways that questions come to us through our website, through our YouTube channel. Wherever they come, we like to kind of essentially answer them. And underneath that, we're going to talk today about, when we talk about metallic or sensors for metallic elements, I'll talk about ion selective electrodes, and I'll also talk about others, which is really ASV or anodic stripping voltammetry. Question number 4 is really about gluconate and how to make a sensor for gluconic acid or gluconate, and I will mention that. And then also question number 5 here is about using a pH sensor. So with regards to question number 1, if you want to measure the capsaicin, for example, in a chili, this is the molecule here, you can measure it on HPLC. Some people like to do panel testing. I don't it's just not good. I mean, this is what people are doing. It's very subjective. Everyone wants a really objective test. Problem with HPLC, it's large, bulky, expensive, full of organic solvents. You need a good laboratory. They need high maintenance. There's lots of reasons why people actually don't use HPLC. And then there's food sense, which obviously we manufacture. So, but the food sense is really a sort of version or a food equivalent to a glucose meter, where you take an electrode and you put a sample on it and you get an immediate result. So it's really similar to a glucose meter, and that's kind of, homage to ZP's origins as well. Now, in terms of when we were first developing the food sense, we needed to validate it. And so what we would do is test it against HPLC. But in doing that, you then discover lots of things about HPLC, especially HPLC applied into the food industry, that are not always so well understood by people. So we made sure that we were kind of correlated with HPLC. So if somebody took a sample to an HPLC and got what's called a SHU, a Scoville heat unit, and they took it to our meter, they would get, the same result. So, we made sure that we were sort of validating that. But in doing that, you really discover a lot, actually. You discover that when you talk to people in industry and academia, they don't always understand the difference between accuracy and precision. So I'll just kind of sort of touch on that and say, look, everyone talks about accuracy and precision as if they're sort of interchangeable terms, but they mean something quite different. If I have an analytical technique that is accurate, then there's a sort of truth out there. For example, the pH is 5 and I measure it and I get pH 5.05, pH 4.95, pH 5.01. You would describe that as accurate. If I did that again and I actually got results that were pH 5, pH 4, pH 6, overall I could describe that technique as accurate because I could do all three measurements, average them, and actually find out that I kind of essentially got an accurate measurement, but they were individually quite imprecise. Now you can have inaccurate but precise. So let's say the pH was 5 and I measured it 3 times and I got pH 6, pH 5.5, pH 6.5. Let's say they were all sort of clustered together, but they weren't actually on the pH 5. I would describe that as precise but inaccurate. Now with precise inaccurate, you can actually use what's called an offset, because essentially your analytical technique has an offset from the truth and you can essentially subtract it. So that's fairly easy to fix, let's say. The one that's hardest to fix is inaccurate and imprecise. Essentially every time you make a measurement, to be ridiculous, for example, the pH is 5, but I measure it, I get a 6, I get a 3, I get a 9, for example. You would describe that as inaccurate and imprecise, and very hard to fix. You just have to get, essentially work on your operating procedure or work on the repeatability of your sensors, for example. So it's nice to be accurate and precise. People don't understand it, but you can be accurate and precise, but you can also be inaccurate. You can be accurate and imprecise. You can be inaccurate and precise. Accurate and imprecise you can fix by just doing more measurements. Inaccurate and precise you can do by doing an offset fix. So I love those two terms, accurate and precise, because everyone says, oh, I want accuracy and precision, but you really have to sort of, what is your definition on those words? Now, something that we've discovered is that people, for example, really believe in taking their chili powder, for example, getting it measured in a lab by HPLC, and they get a certificate of analysis, and they go, that's really good. Now, our conjecture is that actually if you took the same sample, sent it to a different lab, or take the same sample and take it to a third lab, you're actually going to end up with 3 different results. This is something that's really not understood. Well, it's not. No, it is realized by some people in the food industry, but not necessarily by everyone. So you could describe this as being, maybe they're all accurate in terms of they're all centered around the truth here, and it's only by averaging them that you'd actually get to some sort of accuracy. Now, what's even stranger, can I say, is actually if you took the same sample and sent it on 3 different occasions to the same lab, you'd probably end up with different results as well. The reason I bring this up is because when you're developing sensors, biosensors, methodologies, there's sometimes the gold standard that you're told about. But when you dig into it, you find out the gold standard is not quite as golden as you would have otherwise thought. So just be a little bit careful, because people will sometimes challenge you as a scientist, will say, this is the truth, when actually the truth is not as golden as people would otherwise like to believe it is. Question number 2. This is a really interesting question, actually, because Chemiresistors, I'll sort of dig into it a little bit, but in a chemiresistor, in the simplest form, you'd have 2 electrodes. You would be measuring the resistance between them. You put an electrolyte between them, and this electrolyte is often solid. I mean, chemiresistors, we're often using chemiresistors in gas phase. So you have an electrolyte between 2 electrodes. Some sort of gas comes in, it interacts with the electrolyte, and the resistance changes. and therefore you call it, a chemiresistor, and you hope that the resistance changes with the analyte of interest. Now you can apply essentially an offset voltage between these two electrodes. Now, if somebody came to me and said, I want to make a chemiresistor, I'd obviously, I would suggest that you took one of our screen printed electrodes. Any links, as I say, I've put them underneath the video as well. Anyway, so you take one of our electrodes. I'll just describe that. You could actually make an electrical connection here and here. We do have connectors, by the way. I realize they're not in today's presentation, but we definitely do have connectors. And you can essentially measure the resistance between these 2 points. Now that's no good at the moment because this is just in air, so it's got infinite resistance. But if you put your electrolyte or your sensing material sort of in a small square here between these 2 electrodes, now hopefully in the presence of the analyte, the resistance will change. You didn't have to use these 2 electrodes. You could have actually sort of covered the whole thing. Just note that I'm ignoring the middle electrode at the moment. You don't have to, by the way. You can take advantage of that. And now you can just do a simple sort of 2 probe and resistance measurement between these 2 connection points here. But also you can actually take advantage of all 3 electrodes. And this is something that we've done where we've made a chemiresistor, and we're sort of treating it a bit like a transistor, because we're able to apply a voltage on the 3rd electrode and sort of put energy into that electrolyte, and it can end up changing the resistance and change the sort of sensitivity of our sensor. So what I'm saying here is chemiresistors can be built on screen printed electrodes. I think screen printed electrodes is a good platform for people. Otherwise, you are facing kind of glass substrates with gold sputtered electrodes on them. It's really expensive way of manufacturing. It's not at all scalable. For example, we're selling a sheet of 300 of these kind of electrodes, and they're sort of 250 euros, which really makes it less than a euro each. And the biggest problem at the moment is actually shipping costs, but shipping costs are sort of essentially non-linear, that the more you buy, the relative amount of shipping costs actually doesn't go up. So you can make chemiresistors. You can do it by sort of putting your electrolyte either just between 2 of the electrodes or over all the electrodes. You can do a sort of essentially a 2-point measurement of resistance, but actually you could do a 2-point measurement essentially of resistance, but also use another electrode to actually apply a voltage offset. And then I think you're getting closer to a more standard electrochemical measurements. I think chemiresistors, they're good. We use them ourselves in gas phase, but there are techniques which can be augmented or can augment chemiresistors, which is things like impedance spectroscopy, where you're measuring that resistance as a function of frequency as well. I think you can get a lot more signal and information out of the system by doing that as well. So I just want to say that we would cover most of these techniques in our workshops. So at the very beginning of this, I said there is a link. We have some workshops in April and May, for example. I really suggest that, especially people who are in industry, come along to one of our workshops as well. We're always really good at understanding what people who are coming to the workshops are actually trying to achieve, and then essentially tailoring the conversations and the presentations around that, in real time, as we understand what people want to achieve. Something that I want to just highlight is, in lots of our old videos, you'll actually see us using anapots and anapot EISs. And we actually have something called EMMA these days, which is a multi-channel potentiostat. It's absolutely tiny, but it actually can run 6 electrodes or 6 sensors at a time. And that's important because the problem when you're doing sensor development, especially with things like chemiresistors and impedance spectroscopy, you do need enough data to really make sort of sense of your data. This happens to us all the time, that we'll do an experiment of 6, 5 of the experiments are good and they're sort of consistent, and one of them is a bit of an error. Well, it's okay to reject the error because we've got enough data to say, that sensor, we just had either a bad sensor or we did something wrong in the experiment, but 5 of the experiments were good. So we could be more confident in the one. Problem is when you're running one experiment, and you get that result, you don't know, well, is that the truth or was that just an error on my behalf? So I just want to highlight that we do have this multi-channel potentiostat. The link is underneath the video as well. This was a nice question. It came through the YouTube channel. So, somebody was asking us, do we have sensors for metallic elements? And it was too big a question to then respond on that YouTube, because actually what is meant by metallic? Metallic can be metals that essentially in what's in there called their zero oxidation state, or it could be metals that are oxidized. Now, we've got lots of ways. So for example, if somebody said to me, can you detect the metallic iron, potassium, calcium, sodium, for example, then we definitely can. And I put a quick link there. These are really using iron selective electrodes. If you have questions about what I mean by an iron selective electrode, please put it in any kind of comments or message us through the website, or contact us through the website, and we'll mention it. So when people say to me, can you sense metallic elements? The answer is yes. Now, the reason that potassium, calcium, and sodium, we do them by iron selective electrodes, is I realize the other technique that I'm going to discuss which is anodic stripping voltammetry. These elements are so reactive that we can't detect them using another technique, because every time we try to, for example, reduce potassium, sodium, or calcium back to its element, they're so reactive, we're just not going to do it. We're going to end up doing the hydrolysis of water before we can actually end up putting an electron back into any of these elements. So, but with metals like copper, lead, palladium, platinum, precious group, platinum group metals, and we can use something called anodic stripping voltammetry, where we have our ions. We essentially plate them onto an electrode. When I say an electrode, I mean one of our screen printed electrodes. And then we can actually strip those ions, or that metal rather, back off. And in doing so, we pass a current, and the current was proportional to the amount of copper that, for example, in this case, that was originally in the sample. This is a sort of realization, or what we do it in reality. We have these kind of electrodes, sensors. We put them in the meter, and we have an app. The app drives the meter. We have something called the Julie database. So sensor goes in the meter, sample on the sensor, app runs the meter gives the data back to the app sends it to Julie, and then we get in there, we process the data so that people get millimoles, or sometimes in these kind of more industrial applications, people are interested in units like ppm, parts per million. So the quick answer to, do we have sensors for metallic ions, or metallic elements, I should say, that was a specific question. The quick answer is yes, we do. You can see that it's too much of a nuanced answer to be able to just answer it through a YouTube messaging. But I put a link to this technology as well. So every time the link pops up, we'll have put it underneath the video as well. This is a question that came in about a week ago, the detection of gluconic acids. So can you make a sense of the detection of gluconic acid? I just want to make sure that you understand that I got this from this particular paper. I can see what they're doing, because what they're doing is they're taking their target here is gluconate. They say GK here. GK will stand for gluconate kinase. A kinase is a molecule that will transfer a phosphate onto another molecule. So what they're doing is they got gluconate. They react it in the presence of a kinase enzyme, in the presence of ATP, adenosine triphosphate, and that puts a phosphate group onto the gluconate. So now we've got 6-phospho-D-gluconate. That then reacts with this gluconate dehydrogenase, this GDH molecule here, in the presence of, and I should have made this a bit more clear, in the presence of the cofactor NADP+. This all sounds very complicated, but actually we do this kind of stuff, how do I say, all the time at ZP. So we would take out our electrode, we would actually make a formulation that contained the enzymes. So there's 2 enzymes here, there's two cofactors, ATP and NAD+, and we would immobilize a solution of that and dry it onto our electrode, and that's how we would start making this gluconate sensor. And this is what's so good about electrochemistry, actually, that you know, this paper was electrochemical, so these guys have already proven the point. And to make a sort of product from that, you literally need a good quality repeatable screen printed electrodes. And that's you know, how do I put that? That is the problem, that actually there are not good quality screen printed electrodes out there. I'm super biased. Ours are really quite good. So because we use them the most of anyone in the world, we're the biggest consumers of our own electrodes. But to make that kind of sensor, you need these two enzymes, these two cofactors, and then there's a little sting in the tail, because you need to interact with this NADH molecule. I can't remember what mediator they're using, but for example, we would use something like Maldala Blue mediated enzyme in order to interact with that NADH, and I put a little link to that here. Question number 5 is about pH electrodes. So at ZP, I think, what's the most measured chemical parameter in the world? It's actually pH. So everyone is always measuring pH. So it's nice that somebody's got our pH sensors. Appreciate that. How about storage? So our pH sensors, I would describe them as inorganic. So we do tell people keep them in a dark, dry, cool place. That actually describes a fridge, because a fridge, you know, the door is closed, so they're generally dark. It's dry because actually the moisture in the air is, you know, essentially kind of frozen out as ice, so they do dry. And then they're actually quite cool fridges as well. Obviously, they're sort of 5 degrees C. So, for example, so storage. Now, do you really need to do that? No, you don't. But it's easier to say keep them in the fridge, because then you're not leaving them in the direct sunlight. You know, direct sunlight would be a disaster. It would probably end up really oxidizing and corroding the reference electrode. I have recently seen. We sent some electrodes to India. They were kept in a dark place, but actually India is can be humid and it can be hot, and the electrodes corroded. The silver chloride corroded. It looked like it formed silver oxide. So, out of an abundance of caution, keep them in the fridge. The conditioning process is kind of interesting, because I've got a video in a minute, and you'll see that we don't condition; we just use them. And then they were asking about. Do they need to condition the reference electrode before use? I'll show you a video in a minute, and the answer is no. Do we need to? What's the conditioning solution time and repetition frequency? I mean, we reuse our pH sensors a lot. People always ask us, what's the lifetime of your sensor? And the question is the answer is, electrochemical sensors and biosensors are unique in the sensor class because they're in intimate contact with the sample. So, if you were continually measuring something at pH 1 or pH 10, these are quite extreme pHs, you're probably damaging materials, so that would be a limit the lifetime. But we use our pH sensors for a long time. I don't think we really ever break them. I think we just throw them away at some point, or they get lost. How to properly store sensors? When you store sensors, you'll see that in the video that I'm about to show, that Andre has a little wash bottle of DI water. You know, he rinses them down. What we would do is we rinse them down just to get rid of all the pH solution. We'd probably lightly tap them with a bit of tissue to sort of suck away any water, and then we would store them in the fridge. So if you want to gather data like this, there is a video online, and I think actually it's even in this link here. Now, this video is quite an old video, but you can see, and you know, it's on an old format of ours, but you know, he has this pH sensor, you know, plugged into the potentiostat. He's using the Anna pot there. What you'll see is he's going to run he's going to run in what's called open circuit potential mode. He's got 3 solutions there, and all he's going to do is he's not really going to do any conditioning. He's actually just going to in a minute, he's just going to put them in one of the solutions and get a result. Now this software that he's using, it does have a pause function, and it would probably be better if he paused, because every time he goes between beakers, he gets all this noise because the sensor's essentially just out in the air. It doesn't know what to do, and so so if you want to get sort of essentially nicer looking data, pause the software whilst you're moving between sensors. But here, I don't know, for whatever reason, he's decided to rinse it down. He's going to put it in one of the pHs here. So at the moment, the sensor's sort of, it's doing something crazy, but now he's probably gone into solution C, because now he's going to get a sort of sensible pH. He's probably just talking away there. That's fine. And then in a minute, there we are. He's rinsing now, and he's going to go to another pH. I would suggest you pause the software at that point, because otherwise you're going to get all this crazy noise. And then he goes into another pH solution here. That's why I found the questions, it's literally this crude is what we're doing. So I can see that this plateau here would be one of his original pHs. Then he moved it, so he got all this crazy noise. And now he's in another pH. And what I would suggest actually is he'd pause the data capture whilst he was moving, and then the data would essentially looked nicer. And now he's obviously rinsing again, and then he's going to go into the next pH. So to get nice looking data like that, we literally would do it this way. You can also just do it by pipetting onto the sensor as well. So now he's at a different pH, and it's plateauing away. To get the nice looking data on the left hand side of this screen at the moment, you want to pause the data capture in between this movement and this crazy rinsing. Otherwise you just get this noise. So this is saying the same thing in the same way. Sensor in solution, run in open circuit potential mode, you get a plateau. I would suggest you sort of pause the software. You can change the pH, start the software up again, you'll get a new reading, go back to the original pH, and you should come up pretty similar result as the first one. So pH sensors are quite robust. Keep them in the fridge, rinse them after use, dry them very lightly with a bit of tissue just to get rid of all the moisture, and then put them back in the fridge when you've used them. Watch that video a few times. You can see that these things are quite robust. You should essentially be okay. Right, so accuracy of HPLC. HPLC is a great technique, especially when using the pharmaceutical industry, but in more things like chilies, which are very heterogeneous samples, it can actually be not as accurate as people think. Chemiresistors, you can build chemiresistors on top of screen printed electrodes. I would generally suggest it because I think it's a much lower cost platform for doing that. Sensor for metallic elements. Yes, we do have sensors for metallic elements. We have sensors that fall into the ion selective electrodes category, and also ASV, anodic stripping voltammetry. That gluconic acid or gluconate detection, it's two enzymes, two cofactors. We would describe this as an enzyme cascade, where one enzyme reaction cascades down to another enzyme reaction. Then we get this cofactor. In that case, I think it was NADPH, which means you need a mediator on the electrodes. But nice thing about electrochemistry is there's always an academic paper to sort of back, there's somebody's always done it. There's a massive gold mine, if I could put it that way, of academic literature out there. And then using that pH sensor, follow that video. It's not so hard. And don't forget, if you really want to get great confidence, great background in biosensors, electrochemical sensing, IVD development, don't hesitate to come to one of our workshops. So I just want to say thank you for all the questions. You can see we definitely give all these questions a lot of thought. We make up, essentially make materials in order to try and present it in the most concise manner. So if you have any questions, don't hesitate to reach out to us at ZP. Otherwise, we're getting close to the weekend, so I wish people a good end of the week, and I will speak to some of you in our blog on Sundays at 8 AM London time, and some of you on Thursday next week at 8 AM London time. Okay, take care, and thank you so much. Bye-bye.